Hi, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and we are at the topic number 5, which is regularization. So, regularization is basically the techniques to prevent overfitting, and it's a very interesting topic, and there are quite a few concepts here. So, this video, which is 5A, covers the basic concepts of regularization, and of course, there are other sub videos also for regularization. And this video and other videos are developed using the personalized learning management system, which is available at www.easymcq.com/GoGet. So the approach which we have adopted in this course is content delivery. And this content delivery is used by the leading learning management systems. And it has certain wonderful features. And there are millions of users of learning management systems which are based on content delivery. And here are some of the features which are there in such systems. You can read through them and go through them. And these are the 6 features uh, which are used in the personalized learning management system, which are, for example, full scale text search. And based upon that text search, the Q&A of interest can be retrieved. Then it supports people who are visually handicapped, and it supports working in a small space to view, such as a smartphone, and the progress is tracked of the end user. And of course, there is MCQ based online testing and evaluation system, and so on. So there is a link here in the blue color, which is the link to these videos, which show you how to use that learning management system, for which the link is shown in green. And there are two basically approaches. One is the question and answer or Q&A based approach, and then is the traditional learning based approach. So the approach which we have adapted or adopted in this course is a combination of both. So Q&A is proactive, it is engaging, and it adapts to the user requirements, and of course it promotes thinking. And machines are not good at thinking, so we are ahead of them. It promotes that. So this is a blend of these two technologies, the approach or the methodology which we have been using in this course and other courses. So this is the breakdown of the topics which are covered in this course, Deep Reinforcement Learning. And right now we are at the 5th topic, which is regularization. Within that topic, there are 15 questions and answers, and every question and answer is a concept. And these Q&As are divided into 4 subtopics: 5A, which you can see is in yellow color, and 5B, 5C, and 5D in different colors. So we go through each of them as per their difficulty. And without further ado, we move on to the details of the Q&A for this video lecture. So we start with the topic regularization, which is topic 5. So since we are looking at the first 5 Q&A, so that's topic 5A. So we start with the first one. So what is regularization and why is it needed in deep learning? So one thing is to take into consideration that as this Q&A shows that regularization is not limited to deep learning, but it also applicable for reinforcement learning. But the way it is used is very different. So why do we need regularization? And before that, what is regularization? So these are the bullets which are explained in detail here over here. You can go through them, right? So I will go through these bullets and explain this diagram and everything. So what is regularization? So regularization consists of a set of techniques. Okay, that is regularization, set of techniques, and we'll discuss some of those more popular techniques in this video. And why regularization is used in deep learning is to prevent overfitting. Okay, to prevent overfitting, because when there is overfitting, then there's perfect match for the training data, but poor performance for the unseen data, which we don't like. Okay, so this is a common problem with neural networks. Okay, what the common problem that they learn too well. So that too well learning, okay, that too well learning results in overfitting. Okay, and that overfitting basically consists of including the noise as the data, outliers and as the data, so that gives poor performance on new unseen data. So when we do the regularization, okay, when we do this regularization, what we do is that we introduce additional constraints, we introduce additional modifications, and they are introduced during the training phase. Why? Because we want the model to generalize instead of memorizing, okay, data. So if it memorizes, then of course that is overfitting. So generalizing is now remember, generalizing is doesn't mean that it means that it is a good fit, robust against noise. So now deep neural networks are powerful, okay, but they are sometimes over parameterized. Why? Because that parameter selection is automated. So, and of course, they can represent very complex functions because of that parameterization. However, however, without regularization, okay, this flexibility in of selecting, identifying own parameters, that can lead to overfitting using the training data, and that results in a weak or poor generalization. So, how to prevent? So, this let's first look at this diagram here. So this diagram shows that you have this time and you have this value, and this is overfitted because the everything is part of the everything has been recognized as data. Okay, so this basically this dotted line or dashed line passes through all the points. This is overfitting. Okay, because this kind of data is not going to become of or this kind of things for the unseen, right? So after we do the regularization, then of course we have this dashed line which passes close to all the points, and we can see this line is non-linear, more of a quadratic form, not actually quadratic, but more of a quadratic form. So this is regularization, and you can see that these points, they are not considered as the data points. Even this one also. This is a good fit. So regularization results into a good fit or a robust fit. So preventing overfitting. Okay. So regularization helps. It helps. It's not absolute. It helps prevent overfitting. And how does it help? It discourages the model. This is a model. This line is a model. This dash line is a model. Or if and the weights and the training, okay, that is also a model for the neural nets. All right. So that regularization prevents overfitting by discouraging the model, okay, from memorizing the training data. I remember I gave you the example of a baby who recognizes the mother when the mother is going to a wedding party and she has put on makeup. And in real life, at home, she doesn't put on makeup, and this baby can only recognize the mother with the makeup. So that is overfitting. Okay, so how regularization is prevented, right? That is by including constraints, by including penalties, okay, and forcing the model to learn the patterns, okay, so as to generalize better generalization for better generalization for new unseen data instead of fitting very well with all the details of the training set, because the model has been trained to classify not the training data but to classify the unseen data. All right, so by virtue of regularization, generalization is improved. Okay, so what happens is that the learning process. So how generalization is improved by simplifying the learning function or by introducing noise during the training. So basically, that makes the model to perform well on unseen data. So what are the techniques like dropout, which we will discuss, weight decay, early stopping, okay, and these things basically help ensure that the performance of the model remains consistent across different inputs, and those different inputs are the training data and of course the unseen data. And of course the objective is that this should enhance the the ability of the model to generalize beyond the training data. So what is the control complexity?
So what is control complexity is that regularization controls the model complexity. Why? By by number of things, as a matter of fact, by the magnitude of the weights. Now you know by now that what weights I'm talking about. By limiting the number of active parameters. As a matter of fact, part of regularization is to remove the neurons also and their corresponding connections also to control this. So this prevents the model from becoming overly flexible or overly expressive, and because this can lead to overfitting. So that over behavior has to be dampened, has to be dampened. So now, of course, uh, simpler models are more interpretable, they are more stable, and they are less prone to variance in the predictions. But if you like, but this is have to strike a balance, because if you go on doing this, it may, as a matter of fact, result in underfitting also. So the model becomes very, very simplistic or overly simplistic, right? So there has to be a trade-off. Stabilize the training. So now you know what we are discussing right now. This is part of computer science, but this is not this is more of AI engineering. Okay, this is more of this course could be part of a AI engineering course or degree program or AI bachelor's program, right? Because we are going beyond databases. We are working with directly with the models. So stabilize the training in deep neural networks or reinforcement learning. Okay, now training can become unstable, right? Because of large updates or oscillations. Oscillations we have discussed that in the loss space there can be oscillations due to number of reasons, okay? And those functions which are used, and we would like to dampen it, and we use the concept of momentum and other things, right? So what we do is that something which is called as gradient clipping is done, or batch normalization is done, or entropy regularization is done, so as to smooth the dynamics of learning. Okay, we have to smooth the dynamics of learning, and basically we want to ensure that the updates are gradual, number one, and we would like to reduce the risk of divergence or erratic learning. We have seen that divergence can take place, and we would like it to converge, right? So need to stabilize it and enable robustness. So we would like uh, and what the regularization does, it improves the robustness. Robustness means the behavior in the presence of noise or missing data or issues. And how it is made robust? By making the model less sensitive to the variations in the input, which and less sensitive to noise, less sensitive to adversarial perturbations, which we have discussed in the previous topic, adversarial attacks. So we use techniques like noise injection. We also discussed in the last topic that because of missing data and noise, as a matter of fact, this prevents getting stuck in the local minima and dropout and adversarial training, right? All of this enhances the performance. It enhances the reliability. Okay, and even when there are deviations. So these are the these are the how regularization helps. So now most of this material which I am discussing, you might not find this in the textbook, especially the diagrams also, because of the diverse nature of this course, and because I would like to expose you. I would like to increase your exposure. So this is the textbook. Of course, this is the textbook, but there is a lot of other material also available, right? Which I for which you should you should be reading if you're interested in your career in AI. Okay, and you have one of the steps, you have taken the right step, which is you are taking this course of deep and reinforcement learning. So what are the common regularization techniques? So now we are in regularization. What are the common techniques? So these are the techniques. L1 regularization, I will tell you, I'll discuss with you about L1 regularization, L2 dropout, early stopping, data augmentation, and so on. We have a separate Q&A for data augmentation also. So MLP, what is MLP? Multi-level perceptron. Okay, before and after dropout. So this is your neural net before dropout. What is the dropped out? These neurons have been dropped out, have been removed for the purpose of regularization. Understand? So when this neuron is taken, when you have this hidden layer consisted of five neurons, but two have been taken out. Okay, I think this should be five. No, yeah, two have been taken out. Okay, two and five have been taken out. Right. So this is part of regularization to control the overactivity, which we discussed in the previous Q&A. And this over here is the early stopping. So we have this training process, right? And we have this loss of accuracy, and we see that as this gap increases, okay, as this gap starts to increase, okay, training is stopped. As this graph widens, the training is stopped. Okay, so we have the epochs and we have the error, right? So this is for in terms of error versus epochs and accuracy versus. So you yes, we see that the difference is increasing. Okay, right? So this is so these are, and of course there are other techniques also which have been mentioned, L1 regularization and others also. So these regularization are the strategies. Regularization techniques are the strategies which are used in machine learning and deep machine as in reinforcement learning. As a matter of fact, we have already discussed that deep learning is part of machine learning, and of course machine learning is part of AI. So to prevent overfitting, and you know why now what is meant by overfitting. Okay, so it occurs, and you know what is overfitting, right? So among the most widely used regularization techniques are L1 and L2 regularization. Okay, and what they do is that they penalize large weights, because when large weights are added, that has a significant, so that has a significant impact, and that goes through all the layers, right? Affects many layers. So what it does is that it adds a term to the loss function. So we have L1 promotes sparsity, setting some weights to zero. Okay, in L1 sparsity, setting some weights to zero, and L2 encourages small but non-zero weights, so trying to strike a balance. So in dropout, another, which is another powerful technique, temporarily disables random neurons. Temporarily disables random neurons to prevent codependence and improve the robustness, and so on. And there is data augmentation also. I'll show you that what is data augmentation and how it works. So let's now go through these bullets one by one. All right. So first is L1 regularization. So what L1 regularization does is adds a penalty equal to the absolute value of the weight to the loss function. So I'll show you the expression also. And L1 encourages sparsity. Okay. And why and how? By driving many weights to zero. You set the weight to zero. Okay. So the impact of that link would be gone. It would be similar to like a dropout. And basically, so it like the effect is like performing feature selection. So if you put the weight zero, then the impact is gone. So this what it does, it simplifies the model. And when the model is simplified, then the overfitting is prevented. And this is true for high dimensional data settings, right? And then is the L2 regularization. So in L2 regularization, uh, it penalizes the squared magnitude of the weights, square of the weights, right? And discourages large weight values and force them to zero, right? So in L1, right, we are driving many weights to zero, okay? And over here in L2, we are again forcing to zero. The objective for both is to make that function smooth, to evenly distribute the weights, and of course, prevent overfitting, make the model simpler. When the models are simple, they will generalize better, okay? While maintaining the all input features. All right. So let's look at dropout regularization. So what is dropout regularization? So dropout, this is the picture of the dropout regularization. It randomly deviates a subset of neurons during each training iteration, randomly. Okay. So what is the benefit of random deviation is that it is more likely to get out of the local minimum. So this prevents the network from becoming overly reliant on specific neurons. Because if it becomes overly reliant on specific neurons, okay, then of course it is going to start to memorize. You want to prevent this, and you want to force redundancy. and you want to force or encourage independent feature learning because you are randomly removing them. At the time of inference, all neurons are used, right? But not at the time of training. So this results in a robust and generalized model. And then is the early stopping, which we discussed. This is early stopping. So the training is stopped. The training is halted. The training is stopped. Okay, when the model's performance starts to degrade, even if training loss continues to decrease. So it prevents overfitting even before the model memorizes the noise in the training data. So that kind of balances the model and it makes it more generalized. And then finally is data augmentation. So basically artificially increase the training data set, right? By maybe say for example adding rotations, flipping, scaling, shades, colors, uh, uh, gray scales, and so on. So what we are doing is that we are exposing the model to varied examples. We are trying to improve the generalization. We are trying to improve the robustness without additional real world data. Usually, this is done for image processing and image cases, and I will share them with you. As a matter, there's a Q&A on data augmentation. So as before, here are the details. You can go through those details, right? And here are the references if you are interested in reading more about it. All right. So now we move on to the uh, deep learning versus reinforcement learning regularization.